Hi, this is Dr. Samir Ben Osman, and in this video we're gonna talk about some examples of engineering specialties and the way they think. And with that, let's start with civil engineering. So what is civil engineering? Civil engineering consists of designing and building structures for residential homes, commercial buildings, infrastructure like roads, bridges, tunnels, airports, train stations, dams, as well as like industrial buildings that include nuclear power plants or plants of some sorts, chemical plants, etc. It starts with gathering building requirements or specifications, such as the size of the building, shape, capacity that's gonna withhold, etc. And these come from the architects as well as the city planners, etc. And these will be adapted to the topography and the geology of the site that they will be built in terms of the soil, the ability of the soil to withhold the structure that it has, etc. And this will help estimate the loads and calculate the loads. The loads basically needs to be more than enough to support its own weight, which we call the dead load, as well as what it will host, which is the live load. It also needs to resist environmental loads such as vibration, wind, earthquakes, etc., as well as the elements, temperature variations, precipitations, salt water, etc. So once these calculations are made, they will inform the calculation of the size and type of the foundations and structure that's going to be able to solidly support the building and all its loads. In addition to these steps, for large building structures such as bridges or skyscrapers, simulation in computer is necessary in order to study the behavior of the building structure when subjected to the loads. As you see here, for example, these two buildings are subjected to increasing amounts of wind and seeing how they behave. And then the design, the calculations are refined accordingly in order to find the best design that's going to withhold the stresses, etc., before the actual construction. So this is kind of a very quick overview of civil engineering. So let's talk now about mechanical engineering. So mechanical engineering consists of designing, manufacturing, and maintaining mechanical systems that range from keyboards, toys, kitchen appliances, tools, to medical devices such as respirators, dialysis machines, to surgery equipment, all the way to engines of all types, cooling and heating equipment, hydraulic systems, power generation equipment like turbines, generators, and many more. So product requirements include the allowed volume, the input and output, the reliability that's required before needing to repairs, that's called mean time between failures, cost, etc. And once we have identified the specifications that we want, then we move into the simulation. And the purpose of the simulation is twofold. Is to make some designs and then test their performance, and also test the ease of their large scale production. And so based on these, the mechanical engineers will simulate the functioning of the mechanical system in computers, and then they will go into a trial and error process. Basically, they will start with the concept and design, they will simulate, and then they will refine, find some errors, refine, and so on and so on, until they find the design that's optimal. And now they're actually increasingly relying on using machine learning and artificial intelligence in order to simulate millions of possible designs at once, and then find much more quickly the designs that work better. So once the designs are selected, they will be then produced in a small scale in what's called prototypes. So small scale kind of products, and they will be tested in conditions as close to the real world as possible. In order to again find potential ways to improve the performance, as well as improve the manufacturability at large scale. And so once that is done, then the design is agreed upon and moved into large-scale production. So this is kind of a general overview of mechanical engineering. So let's talk now about chemical engineering. So chemical engineering involves the manufacturing through chemical processes of products that are very broad in nature. So it can include prepared foods, pharmaceuticals, cosmetics, cleaning products, construction products, biomaterials, petrochemicals, adhesives, agricultural fertilizers, and many more. So chemical engineering is like a very broad engineering specialty. So chemical engineers, they translate chemical processes that have been developed in a lab, and they move them into a scaled commercial production processes. So they take the product requirements, just like civil engineers and mechanical engineers. So they take product requirements such as the composition of the product, the expected output volume of its production, the cost of the production, the government regulations relating to the safety, etc., to determine the choice of the processes, the materials, and the equipment that they need to use. And then based upon that, they will design the blueprint for the production as a succession of 3 types of modules. You have unit operations and unit processes, where specific steps are performed, such as filtration, drying, oxidation, etc. And then you have transport units, which basically serve as links between those modules. And so they consist of pipes and pumps and things of that nature. And all of these are designed to ensure uninterrupted production of the product. Once the design has been refined in a trial and error manner many times, then they move into actual production. So they produce the chemical plant. And then the chemical engineers will also include the responsibility to maintain proper operation of all these units between them. So that's kind of a quick overview of chemical engineering. So let's talk now about electrical engineering. So electrical engineering is like a broad specialty that has many subspecialties. I'm gonna just kind of select 4 of them. And the first one, which is kind of proper, let's call it pure electrical engineering, and that's kind of the design and development of equipment for electricity, the generation of electricity, and the transformation of electricity, and the transport of electricity. So electrical power is generated using solar power cells or rotary devices called turbines that turn by the action of the wind or the water or the steam, and the steam can be generated from either burning fossil fuels or from nuclear fission power. And so these turbines, in turn, they rotate what we call electrical generators that operate on the principle that moving magnetic fields move electrons, as we saw in the principles of engineering. And so as such, generators are made of an axis of magnets that rotates within a cloak of electric wires, thereby making the electrons in these wires move and thereby generating electric current. That current is then distributed using high power electrical lines, and high power is more efficient at transporting electrical lines than low power because it has less loss. And so once those high power come close to the consumer, they are transformed into low power by transformers, and then they will be distributed to the consumers, which are the homes, businesses, the factories, etc. And they need to exactly match the demand in real time. The reason for which is because electrical power at this scale cannot yet be stored. So we don't have like batteries that store, thousands of megawatts. So we have to adapt exactly to demand. So the whole electrical power plant to consumer network has to be very finely tuned. It cannot be overpowered because it's gonna damage the transformers and wires, etc. And it cannot be underpowered because you will have power outages. So managing it is like a very finely tuned dance. So in addition to that, I want to talk about another subspecialty of electrical engineering, which is electronics. So electronics focuses on designing and building systems that modulate electrical powers, electrical signals to transform inputs of various kinds. For example, voices in microphones, images in cameras, data in computers, etc., into desired outputs that range from amplifying the voice, if we're talking about a microphone, operating switches and valves, performing calculations, and basic other operations. Now, those basic operations can be also integrated into much more complex circuits. But the basic components of electronic circuits are basically components that either control whether the current passes or not, and they're called diodes and transistors, or components that briefly store a little bit of electrical current and then release it, and they're called capacitors, or components that slow down the current, and they're called resistors. And the combination of these electronic circuits is often orchestrated by what we call microprocessors, which contain a very high number of transistors to power or process logical operations. So additions, subtractions, and operations, or operations, and which are either hardwired to perform specific tasks, such as the ones found in electrical appliances, etc. So they can only, microprocessors can only do one type of operation, or they can be flexible enough to be programmable via computer code to do bespoke tasks and to be kind of flexible enough. So this is kind of a general overview of electronics. Third subspecialty I want to talk about is control and automation. And basically is the design of systems that monitor specific parameters in cars or planes or spacecraft, such as speed, altitude, pressure, etc., and subsequently control devices that maintain those parameters within acceptable boundaries, or we say to maintain them in a nominal state. And so they can control valves, they can control brakes, they can control actuators or motors, etc. So these control systems are critical to automate parts of the functioning of devices that are either hard to monitor by a human being or impossible to control by humans just due to their required precision. They require very high precision, or they require very high frequency of control. So they can be processes that need to be controlled by the hundredths of a second. So human beings are not capable of speeds like that. So that's why control and automation comes into play. And it's the whole kind of a specialty of designing and maintaining these systems. The last example of subspecialty of electrical engineering that I want to talk about is telecommunications, which is the design and operation of structures that encode information into electromagnetic waves, and then send it, and then decode it, and then enable the telecommunication. So this includes mobile phone infrastructure, includes internet infrastructure, includes all the antennae, relays, servers that enable the telecommunications to occur. You can see here an antenna for cell phones on the right and servers on the left. It also includes designing and developing radars, navigation systems using satellites, all of this using the properties of electromagnetic waves to carry information. And this is all kind of the theory of information era that we're going to briefly touch upon in the computer science video. And obviously telecommunication happens either through wires or wirelessly. So the last example of engineering that I want to take here is aerospace engineering, which consists of designing and building anything that goes into the air and space, basically, which is, airplanes, helicopters, remotely piloted aircraft, drones, rotorcraft, spacecraft, including satellite launching vehicles, the satellites themselves, as well as like missiles and rockets, etc. So all of this goes within aerospace engineering. So designing an aircraft or spacecraft always designs with gathering the requirements or specifications. So the carrying capacity, the speed, the altitude, the range, etc., the cost, as well as the regulations, etc. And then trying to make those specifications as quote-unquote smart as possible, i.e. simplify them as much as possible to avoid having to design parts that shouldn't even exist in the first place. Based upon these specifications, the design of the craft will be made by multiple specialized teams. Each one will focus on a part of the aircraft. So it could be the structure, for example, designing a light yet resistant structure for to all the stresses and loads of weight and motion. Also the aerodynamic that it has to have to penetrate the air with the least resistance, etc. And you can see here the structure of a small airplane. I think it's a Diamond airplane. It's a brand Diamond. You can see the radar inside of it as well. So the radar part is called the avionics. So all the computer systems for navigation, the craft autopilot, the communication, etc. And then you have also teams that also specialize in propulsion, which has to be kind of sufficient to push the plane or the aircraft or the spacecraft. It has to be efficient and has to be easy to maintain, reliable, etc. And also teams on that work on insulation and so on. And so the goal here is to reduce the complexity of the design, so that basically, the adage goes that the best part is no part. So if you can simplify as much as possible, you're going to make your design easy to produce and easy to maintain and less likely to fail, while making obviously the product easy to manufacture at scale, because manufacturability at scale is very important and it needs to be thought of while we're in the conception and design phase. So then when we have designs that have been optimized, they get then simulated in a computer program to see how they fare in the stresses and loads that are applied to them, winds, torsion stresses like in movement, etc., aerodynamics. And then they will continue to refine those designs until they reach a good compromise of design simplicity to performance, etc. Then after that, we move into prototypes or prototype building. So the team's going to build prototypes that are scaled down, and they will be subjected to all types of tests. You can see here in the image above a scaled down prototype of an aircraft subjected to a wind tunnel, where they can see how it fares aerodynamically, and then they can make adjustments. And then after that, they move into kind of real world flight tests. So with a real world prototype that's actually capable of flight. And then they run test flights continuously, and they refine continuously. And you can see in the bottom picture a test flight for a passenger aircraft. And you see the computers that are here that simulate all types of loads. And they're also, like below, they will have liquid reservoirs, water reservoirs, to simulate the weight. And they can actually shift the liquid forward or backwards, etc., to see how the airplane behaves. And they will do continuous testing on the different regimes until they have enough data to submit a request for certification by the aerospace administration. In the US, it's the FAA, the Federal Aviation Administration. And once they get certified, they can move into mass production. So I hope this gives you a good idea of the way of thinking of engineers in several specialties. This is the end of this video. I welcome your comments, and I'll see you in the next video. Thank you so much for your attention.